questions below, and I'll respond quickly or in the next episode of Louis.
Hey Meredith, oh my gosh, I'm all zoomed in. I'm on the wrong screen. Hey, how you doing, Meredith? How is your day going? I've been trying to get my Pearson fixed, trying my darndest, and we're all zoomed in. We're waking back up Mubot. Went and got some coffee, working on my Pearson. Got some Chick-fil-A. Nice. What are you working on? What questions do you have? We're gonna try to get my Pearson working. We've been trying to get my Pearson working. It's like sinking even worse now. Hey, Leah, good to see you here. My Pearson person contacted me back and they didn't fix it. It says it's sinking. Like, I'm seriously about to delete all the assignments and I'm like, is that just gonna wreck all the old grades? I might need to do it like late at night when no one's awake so they don't see the grade changes. Like, I have no idea why it's having so much trouble. It just does not want to fix itself. Hey, Lachey, good to see you here. Yeah, of course. We're going through some problems. Which one do you want to work on? Which quiz question? What do you want to work on? So the grades are there. So don't, some people are like, wait a minute, the grades, they're still there. The grades still exist. Great job at the Lachey level. I love it. Or no, you're at the Magnificent Moira level. So, all the grades still exist. It's just that we can't get them into Canvas yet. Sad times. Why? It's the first semester I've ever had this issue where it just stopped syncing. It's like it won't sync anymore. Like, I could manually upload grades. I would just turn off the sync and have to manually do it every time. So it means your grade would not be. Is this? No, that's a different thing. That's just a. I get so many people asking, like, do you want our book? And I'm like, no, I'm good. I don't need your book. So many, when they hear you teach students, yeah, there's been a problem. Which one? It's the grades are not updating. They exist, but they're not like updating. Which one do you want to do, Leah? Chapter 13 quiz? We can do any question you want. Let me know which one to do. We'll do the question. I just literally can't get it to work. Fall Twitter. Oh, man. Man, this is crazy. We're going to see what happens right here. Wait, are we number one? Wait. Is Tennessee ranked number one? Are you serious? We literally are ranked number one? What the heck? That's not a joke. For playoffs. What in the world? So, but I thought we were number two, right? I thought we were tied for number two. When did that come out? No, we'll do the Gallup question right here. Let's do the Gallup. Let me grab that. Oh my gosh. When did this come out? Not for top 25, we still two. So today came out the number one ranking. Number one. That is insane. The only thing that matters going forward is CFB ranking last night, college football ranking. So is that CFB? Is that college football? People are too funny. Oh my god. All right. Let me grab the question. Oh, wait. Wrong thing. Now it's like not launching. I think hopefully it hasn't messed anything up. I think someone's in looking at our course right now or something, because I just clicked and something weird happened. Said like, we're sorry. Your course had a weird issue. So I think they're trying to reset something or doing something. Someone in the background is doing something. Assignments. Instructor tools. Assignment manager. Let's put the first note right here, the first question. Gallup poll. Stat Tool 1, Chapter 13 quiz. The Gallup poll question. So we have a way that we solve these questions. The way we solve them is we figure out what distribution are we working with, and then we figure out... My Pearson is canceled. My Pearson is canceled. It seems to me it is, as far as I can tell. This is Gallup regularly. Here we go. Let's check it out. This is the Gallup regularly question. Gallup regularly does something. Let's check it out. The Cantrelli scale, which asks the respondent to imagine a ladder with 10 rungs. Rung 0 represents the worst possible life, and rung 10 represents the best possible life. Respondents are asked what rung they would say they are on. I'm on 10. 10 out of 10. Responses are classified as thriving, standing on rung 7 or higher, and expected to be on rung 8 or higher 5 years from now. Okay, so you have to say like you're going to be even higher. Suffering if standing on rung 4 or lower and expected to be on rung 4 or lower 5 years from now. Struggling. Sure. So you're either thriving, suffering, or struggling. Okay. In May 2020, Gallup found that the index had reached the lowest level since the Great Recession 2008 at 48.77% thriving, with a sample size of this. Okay, so this is really interesting. And what's so weird is the world we live in nowadays. There's still a lot of suffering. There's still a lot. This is Brian talking about Brian's views on the world. There's still a lot of, starvation, poverty, lots of issues. This question is kind of sad, super sad. But Brian's personal thoughts. Let me tell you about working in a restaurant real briefly. When I worked in a restaurant, worked Cheddar's, a few other restaurants, we throw away a lot of food. And the Great Depression was a really tough time in America where people really didn't have any food to... there's a lot of food insecurity. Even at UT, there's food insecurity. But one thing that I really liked about Cheddar's when I worked at it, I don't know if they still have the same policy, is we had a rule. We had a rule when it came to if you made a mistake with food... You didn't get to eat it, but someone else did, because we're not going to throw away food. So let's say you ordered an extra chicken tender platter because you clicked a button and it went through, and then you bring it out to the table, and before you put it down, because you don't want someone to hit the table and people touch it and stuff, before it hits the table, someone's like, I didn't order that. Well, a lot of times we would do, if someone made a mistake, it would become someone's like shift lunch, because you're not going to throw away food. Now, you don't want to be the person, if you're randomly ordering stuff to get people shift lunches, you're going to get in trouble. So I think some restaurants do it that way, but I was really glad that my managers were like, okay, that can be someone's lunch because it's still good food and we're not going to throw it out. So I don't know. Brian's personal thoughts on this question. Let's look at the question. Explain the meaning of the sample proportion being this. So P hat is the sample portion in context of the situation. So the meaning of P hat right there is the sample portion. This is 48.77% of the people sampled were classified as thriving. This is the researcher's best estimate of P hat. No, it'd be the researcher's best estimate of P. So that's wrong right there. They're not estimating P hat. P hat is the estimate of P. So that looks to be an error when they talk about that. The meaning of P hat is that the researchers have 95% confidence. Ooh, we're not talking about confidence rules yet, are we? That's not Terry. The meaning of P hat is that the researchers have 95% confidence of all people. The meaning of P hat is that 48.77 of the 20,000 people in the sample were classified as thriving. This is the researcher's best estimate of P. Exactly. The proportion of people, that would be all the people thriving. This right here, we're not doing confidence rules yet, but this is the correct wording. Does that make sense, Leah? That when the researchers go out and do this, they take a sample of 20,000 people, we'll just call it 20,000, and from the sample, 48.77% of the sample was thriving, so that's their best estimate of the true proportion who are thriving. So don't worry, we're not doing confidence rules right now, but that right there is the best way to describe it. So calculate the standard error of P hat. So we're going to use P hat right here as the P to do this right here. So what is Q hat right here for this question? If this is P hat, what is Q hat? If this is P hat, what is Q hat? If this is P hat, we're using it just like P times Q over N square root. What is Q hat? What would Q hat be? And so the formula for this will be very similar right here. P, whoops, wrong one. P hat times Q hat. We're going to use the P hat as the P to assume it's the truth. So what is Q hat? If this is P hat, what is Q hat? If this is P hat, what is Q hat? So what would Q hat be? If that is P hat, what is Q hat? P and Q, just like P hat and Q hat, always add up to what? So P plus Q equals 1. Great job, Leah, right there. So they are complements of each other. Great job right there. Jackson, Lachey, sorry. Jackson saw earlier. There we go. Lachey and Meredith, great job. So 1 minus is, oh my gosh. Where's the P hat again? It's right here at 0.4877. So 1 minus 0.4877 is that, times 0.4877 is that, divide by sample size, and then square root. There we go. So the formula was, and wants round to 7 decimals. 1, 2, 3, 4, 5, 6, 7. Oh my, I mean, yes, carry your decimals, but what? So the formula, if you're wondering, I'm going to show it right here. I'm going to write it down next to the screen. So we have the notation right there. The values are 0.4877 is P hat, 0.5123 is Q hat, over 20. So that's P hat times Q hat over N square root equals to that value up there. Does that make sense, Leah, right there? So the value up there is P hat times Q hat over N square root. And we see the value right there. There it is right there with P hat times Q hat over N square root. And the standard error is using P hat right here rather than P. So they're doing it a little bit differently right here, but it's still basically the idea of P times Q over N square root. Explain what the standard error means in the context of this situation. Okay, here we go. The standard error is the best estimate of the standard deviation. Okay, that sounds accurate. Best estimate of the standard deviation of the sampling distribution of the sample proportion, which means the amount of variation in the sampling distribution expected to be seen from the sample of. This seems accurate. The standard deviation is the best estimate of the standard deviation of the sampling distribution of the proportions, which is the measured. I think it's going to be this one or this one. Let me see. The standard error is the best estimate of the. No, it's not the best estimate of the margin error. So it's either C or D. The standard error is the best estimate of the standard deviation of the sampling distribution of the sample proportions, which measures the amount of variation in the sample proportion expected to be seen from sample sizes of this. Correct. And because when you do it, it's based on a sample size that needs to be acknowledged. So this bottom one right here, the difference between these is the first few talk about it being the margin of error. No. And we haven't covered margin of error yet. So margin of error, no. It's not the estimate of the margin of error. It can be used for margin of error, but it's not the estimate of the margin of error. The last two right here do correctly state standard deviation, which the standard error is an estimate of the standard deviation because it's created from a sample and samples create estimates. So right here, you can see that this is using samples. So it's trying to estimate this, which is the true standard deviation for the distribution of the sample proportion. So they're using an estimate right here, and they want you to see that. So this is, I kind of like the question here until I get one wrong, right? Because it's showing you that we are using this right here to estimate the standard deviation. So this quantity we're calculating is the standard error, and the standard error is using the estimates, which is P hat, to try to figure out the truth right there. And then we must acknowledge that we're doing it for a sample size of this right here. So there we go. Pretty good question. Really just a lot of theory. So how's that work right there, Leah? Does that make sense? There's a lot of theory to this question about how they're saying This standard error quantity you see on the screen right there is an estimate because we're using p hat q hat to calculate it. It's an estimate of the standard deviation, which is p times q over n. So they're just kind of showing you that right here to say, oh, that's an estimate. And then it's also based on a sample size, which is acknowledged right there. So using the sample size, it's not for like all samples. It's for a sample size of this. We estimate the standard deviation to be this, and we would call it a standard error then, which is the estimate. How does that sound? How does that look? Pretty kind of tough, tricky question. Yeah, the wording gets I'm triple checking. I'm like, look, you got to look for those small little differences. And p hat is an estimate of p, just like standard error is an estimate of standard deviation. How do you use the mean equation? And then the automatic character recognition. We did one of those earlier. Which one does yours have the fill in the blank wording on it? Or does yours, and how to use the mean equation? Like mu p hat equals p. So in this instance, our best guess of p right here would be 0.4877, but usually a question will state, and I might do more of a traditional one here. This one's very, very traditional. So this will help us right here. Meredith, I'll do this one, then we'll do Jackson's drop-down box one here. Jackson, thank you so much. So this is more of a traditional question right here that I would think would be more like a test question. Once again, I've seen the test many, many times. So Meredith, this will help out with using the mean equation. You ready? So it says here that 51% of people in the US are women. If you took a sample, what percent of your sample would you expect to be women? Oh, no worries, Jackson. We can do it again. It's a really good, tough one. And it's got some tricky answers, so I think we should do it, Jackson. Got to practice, right? Even Brian's got to do a little practice here. So if you took a sample of women, or you took a sample, I said that all earlier today. If you took a sample, what percent would you expect to be women? What proportion of your sample? 51%. So to use the mean equation, which we have right here, let's erase everything we have. To use the mean equation, which we're on this top line right here, because we're doing proportions, is someone a woman? Then we need to know it's a categorical question. So what do we need to know to solve for mu p hat? To solve for mu p hat, we need to know what? To solve for mu p hat, you have to know what? To solve for mu p hat, you have to know what? We want to know the expected sample proportion. Well, we don't have to know sample size yet. We just need to know what percent of the US is women. Does that make sense? We need to know what percent of the US is women, and if 50% of the US is women, if you took a sample, you'd expect what? Now, don't even worry about the sample size. If you take a sample and 51% of the US is women, you'd expect what? If 51% of the US is women, then what would you expect to see in your sample? You expect 51%, right? So you're saying if I take a sample and 51% of the people in the US are women, I expect to see 51%. Does that make sense what that equation tells us? It's like, oh, well, I expect to see 51%. Well, then the next thing right here is the standard deviation. So now we need to know a little more notation. The notation we also have to know is Q. So what is Q currently? If the US is 51% women, then what percent are not women? And that's probably the best way to describe it because when you think about it, P and Q are complements, so we like to use the word not. So we have here not women. There we go right there. So women, not women, 41, 51, 49, math right there adds up to 1. Complements, because you either have A or not A, they are dichotomous. So with this right here, we then need to know the sample size. And they said the sample size was equal to 480. So now we just solve P times Q over N square root. And there we go. I'm blocking the screen. So now we're just going to solve this right here for the answer. P times Q over N square root. Make sure it's not square root of N. It needs to be quantity square root right there. P times Q over N. And then like a quantity square root, not square root of N. Not P times Q over N square root. P times Q over N square root of whole thing. Throw my pen on the ground. So here we go. We're going to copy this. Go back over to the main screen. Drop it in and delete down to 3 decimals. Be very careful. That is going to round up. How many women on average would you expect to see? Well, think about this. So if we talk to 100, yeah, Meredith, like it. So if you talk to 100 women, 100 people, how many women would you expect there to be out of 100? If you talk to 100 people, how many women would you expect there to be out of 100? If you talk to 100 people, how many women would you expect there to be? With this data, 51. If you talk to 200, how many women would you expect there to be? If you talk to 200, how many women would you expect there to be? I'm using easier numbers, then we'll solve it mathematically. 102, because you'd expect 51%. So we're actually doing NP right here, and we're looking at the number of successes. 51 times 480 is going to give us the expected amount. And it says round to the nearest whole number. It doesn't say round up. Be careful. Some do say round up. We are rounding up because it works that way. And that's a really good question. That is, I'd say, a level 3-4 difficulty question. A lot of times how the test is, conditions on the test and such. And Jackson had a really good one towards the end right here, the multiple choice one right here. Really tough question, like very... Truthfully, I'll probably be giving people some points back on this one because it's the way this is worded a little bit. Let's grab the start of it right here and drop it into our notes for today. Really tough question right here. Surprisingly difficult. But I want to talk to you about the theory of this question first. I want to tell you why this question matters and why I'm keeping it, because it does have good theory in it. So when we do the sampling distribution of the sample proportion, we're doing a categorical question. Like, does the device successfully read something? So it either reads it or it does not read it. That quantity right there, 85, is what in notation? 0.85 is what in notation? Hint, it is the percent of time that the card reader successfully reads something. So what is the notation for this? So what is the notation for that right there? 85 is what in notation? What is the notation? That's the percent of time the card reader successfully reads. It either reads or does not read something. So what is 85 or 0.85 in notation? I'm teaching this question to the test right now, like how you should be able to identify things and know how to read things. So what is 0.85 like notation? Like what value should I put? Should I put mu? Should I put sigma? Should I put p? What value should I put? What value is 0.85 in notation? It's P. Great job, Lachey, right there. We got to throw out some points. We haven't done that lately. So it's value of P. As soon as you find P, you should instantaneously find what? So they're saying this is the assumed P. As soon as you find P, you just find what instantaneously? You're like, now I can find this. Q. Great job. Q. So it either reads something or does not read something. Does that make sense? It successfully reads 85% and it does not successfully read 15% of the time. So an X will be the amount of successes in a sample. So X is the amount so we haven't done a sample yet. We will get to sample sizes down here because they're going to run a simulation where they do different sample sizes right here. So here's the thing. Anytime we take a sample, what percent of successes would we expect? Anytime we take a sample, and I'm teaching this to the test, anytime we take a sample, what percent of successes would we expect? I'm going to grab the formula sheet right here and I'll zoom in on it. But anytime we take a sample, what percent of successes should we expect? And the answer is on the screen right over there. Well, so you might be thinking of a rule or condition, Jackson. But for this question, remember it said there's 85% successes. So right here, anytime we take a sample, the amount of successes we would expect is what? So the equation, we're going to use this right here to solve the equation for the expected mu p hat right there. So we're solving for this right here. So regardless of the sample size, we expect we expect the card reader to work what percent of the time. So it's mu p hat stands for expected successes in your sample. How many expected success? What proportion expected successes? 85%. So the sample size right here, what would the rock say about the sample size for this first quantity? What would the rock say about the sample size for finding the mean of the distribution?
It doesn't matter.
It doesn't matter. because it's going to be just, it doesn't exactly. So, but where does sample size matter? Sample size would matter when we're looking at the standard deviation. When you have larger sample sizes, the standard deviation will get wider. When you have larger when you have larger sample sizes, the standard deviation, look where n is at, the standard deviation will get smaller. And let's look at this question, see what it shows. Look at the histograms. What do you notice about the larger sample sizes? You see how this goes from 0.5 to 1, 0.65 to 1, 0.65 to 1, 0.75 to 0.95? Notice that it gets wider as sample size increases, because here it goes from 0.5 to 1, and at a large sample size, it goes from a smaller range. So it's actually getting smaller as sample size increases. It's also becoming more what? And Jackson, this is what I think you're going towards. The distribution starts to look more and more what? The distribution starts to look more and more what? These are the things to learn from this question, the things to learn from the test. And then we're going to get the answers here in a moment. It starts to look more and more what as the sample size increases, more normal. Because if we meet the three conditions, then the distribution will be normal. The three conditions are random. 10% means you sample less than 10% of the total population. Check out off the class day where we went over that. And then you pause because the third condition is based on the data. And the third condition for this is at least 10 successes, at least 10 failures. So check this out. If we have an 85% success rate, how many successes would we have at a sample size of 20? If we have an 85% success rate, how many successes would you expect? With a sample size of 20, how many successes would you expect? Out of 20, we expect 85% successes, so somewhere in here. Look, that's where the center is about at. So you would expect how many successes? How many successes would you expect? So if you have 20 trials and 85% are expected to be successes, how many successes would you have? Expected to see. You would expect to see this many. What is the expected? So this is NP. We're just doing N right here times P. 17, great job, Chase, right there. So we are just taking it, timesing it by 20. And then how many failures would you expect, Chase? Here's some points, Chase. Keep up the great work. How many failures? So don't even worry about solving the mathematics, because you could take your failure rate of 15% and times it by 20, but you actually have 3, right? And think about this, Chase. Successes plus failures equals total sample size. And what do you notice about your successes and failures? They are both not what? Why do you fail this condition? Because to pass the condition, you need what? To pass the condition, you need this. So you just failed that condition. And if you fail the condition, they're not normal. You need at least 10 successes, at least 10 failures, and you just did the calculations to show it fails. Let's do the calculation over here. We can do the same mathematics over here on 50 and go 50 times 0.85, and there's the amount of successes. And you can actually go 50 minus to find the amount of failures. So there are not at least 10 successes there and 10 failures. There's not 10 failures. There's too few failures. But check this out. At 75, when we do the amount of successes, we get this. And when we do the amount of failures, we get this. And both of these are greater than 10. And since they're both greater than 10, how does this look? How does this actually look right here? It looks pretty kind of what? Especially over here. But these look pretty darn what? These look pretty what? The shape of these are what? They look pretty normal, approximately normal. The first one is left skew. That's still a little left skew. This is pretty normal, pretty normal. So those are the answers to the middle questions where we say, or these right here, where is it? There we go. Left skew, approximately normal, approximately normal. So those are the answers to left skew, approximate, approximate. Now, for the spread, we need to look at the range of the data. Sure. So the spread is going to be this one over here. The spread is going to decrease, going from about 5. Here, I'll write this here. Let me show you on the screen. Oops, wrong. Oh my gosh, I'm going to click every button. There we go. Okay. So the spread of this data, we would go right here and calculate 0. Does everyone see how I'm calculating that? Do people see how I'm calculating the spread? Is I'm finding the distance these are away. How are people doing on that? So there's the calculations. And what do you notice about the spread? I'm just looking at how far those numbers are away. And what do you notice about the spread of this? As sample size increases, the spread gets smaller. So that is the formula we just saw previously. Once again, we're trying to connect these ideas to the screen right here, where as the sample size increases, the standard deviation gets smaller. So does this make sense, Lachey, right here? What I'm doing mathematically is I'm just doing, for this one right here, this looks to be about 0.95 minus 0.65 or so. We're just taking the distance those numbers are away right there. So kind of a guesstimate, and this will give us a close enough range. So you notice right here, I'm taking these two values right here and finding the difference, just to talk about the spread of the data. That's not standard deviation, it's just range, basically. Yeah, thank you, Lachey, for asking. Whenever you don't see something, just ask me to expand upon it, and I'll go into greater detail. But that's just giving a kind of a guesstimate of the range. So 0.5, 0.35, 0.3, 0.2. And so when we look at the answers for these, the sampling distribution has so this is wide range for the first one. The next one was 0.35, relatively narrow. So then this one's this one, relatively wide. And then this is relatively narrow. So if you notice, it's getting more narrow. And those answers right there on the screen, the greater than 0.4, the between this range, the between this range, and the less between that range right there. So there's the answers associated and the drawing we did. This one is the scary one right here. But the answer to all of these should simply be what? The answer to where the mean is should simply be what for all of these? I guess with the left skew, still, the answer to all these should still be what? The mean of the distribution should be what? Don't think of a range, just think of a value. And if you send me that you got this wrong and your value is in the range, I will give you the points back. So the mean of the distribution, according to how it works, should just be what? What value should the mean of the distribution be? What value should the mean of the distribution be? What value should the mean of the distribution be? It should simply just be what? What would you expect the success rate to be? Well, that is a wide range, but think of one value. What percent successes would you expect if you had, oh my God, I'm red. 0.85, you would expect, I think it's just the camera, don't worry, it's the camera. 0.85 is the percent of successes we expect. So 0.85. So 0.85 is the key value to look for in any of these ranges. See, 0.85 is in this range. Good right there. 0.85, this is where it gets scary, is 0.85. And if you pick this answer or this answer, I will accept that. Those are fine. And I hate that they're doing this. They really, whoever wrote this and coded this question, no. Because, and then this one has to be that one. So these two are the ones we could possibly get wrong. And is it going to be this one, really? There it is. That is a bit ridiculous. It's 0.85 is the answer for all of them. Please tell me if you get that wrong. Please tell me. This question is great otherwise, but mine is 83. It should be in the range of all. If 83 is the answer right here, then you should see 83 contained within the ranges right there, Jackson. Does that make sense? So, and make sure you're doing the mean, because this is the center, which is the mean, and then this is a measure of the range, which is spread right there. It's doing the range right there. We do calculate the standard deviation for it, but whatever value is the true success rate is where we would expect the center to be. Yeah, exactly. They give you like a ridiculous amount, but the only possible answers are the ones that actually contain the truth. I do not like how they... Oh, because are they having you look at it and be like, that's so crazy to look at. You see, the peak is a little bit to the right. It's but binwidths can change the way things look. So I think they're picking that because the peak is there. So let me redo it and take a look. This is question 10. Let me see if that's the trick to get it. Okay, so I'm gonna look at this one again. Question 10. and see if they're using that methodology for finding the answer every time. Okay, so we become pros at these questions. You want to know the theory behind it, though? Okay. So, well, once again, this is why I want to go through and teach people how to do this, because they're left skew, approximately normal, super wide range, medium range, and it gets relatively narrow by that point. The centers of the histogram are going to be in here. Oh, because yeah, they're picking the bins it's between. So 1, 2, 3, fourth. Fourth bin is where the center's on that one. So this one's obviously there. Fourth bin, I wish they put them in order. So the fourth bin is the 0.65 to 0.775. Wait, 7. Okay. Yeah, they're doing it by that way. 8 to 8.5. And then 7, 7.5, 8, 8.5. Oh, no, it's smaller than that. There it is. So this is the 7, 7.5, 8.5. No, 7, 7.5, 8, 8.5. So this is in the 8.25 to 8.5 range. They really want you to count up the bins like that. The last one right here, it doesn't even go properly on the bins. So that is the 0.8, 0.85, 0.9. So it's even a little, it's in the lower, so whatever, because that's where 0.85 is, what is we didn't even see what the success rate is, 0.83. Yeah, and 0.83 has been those. So this one's easier because 0.83 is in the range. So there we go. That should be right. There we go. I am really red looking right there. So that's how they... No, that's the camera. I'm like, I don't look like that, do I? I'm like, if I do, something's wrong. I don't think... I might go look. Give me 2 seconds. I'm going to look in the mirror. No, it's just the camera. Just the camera. That's odd. Camera does weird things. Well, let's head back to the main screen. Ah, it's not close. Too much. Over here, much. Over here, back. Back off. Magical changing screen. So many things. Ciao. What other questions are there? What other questions are there? Who has more questions? More questions. Has my Pearson contacted us yet? Nice job on the quiz right there. The very similar one. There's a very similar one. Are you talking about the one where it says as the sample size increases? Oh, this is fundraiser one. Great job. Tough quiz right there, Leah. And automatic character recognition, do the other version right here. And this is a tough quiz. Let's do the other version of it. 39, 53, stat 201. Version 2. Automatic character recognition. Here we go. Let's check it out. So this is a very similar version of the question. Look at the histogram, which has small. Yeah, let's do that one next. You got it. An automatic recognition machine has an 85% success rate. That's pretty much all we need to know. So this question, check out the version 1 we just did, because what they're asking you to do right here is to figure out when you believe it's normal. When you believe it's normal. How would you check to see if things are normal? So this is review notes from today. What would you need to know to make sure it's normal? To make sure it's normal, You need to check what? These are the notes and how to solve the question. What do you need to know? Technically all three. The conditions, exactly. So let's start looking through the conditions on this. Well, we'd have to assume that these were randomly collected observations. We also have to assume it's less than 10% of the total sample. Great job, Meredith and Lachey right there. Great job. Now, the one we really need to solve for is that there's at least 10 successes, at least 10 failures. So let's take a look right here at the data. Well, if you notice, it starts to look maybe normal at 50, probably normal at 75, and definitely at 100. As sample size increases, it becomes more normal. If the success rate is 85%, which is P, what is the failure rate? If the success rate, which is P, it tells us in the question is 85%, says it right there, 85% success rate. What is the failure rate? It's 15%. So that's where the issue is probably going to be because there's more successes. So let's check the amount of failures. There must be at least how many failures for us to meet the condition? How many failures must there be for us to meet the condition? As I'm checking this right here, I'm seeing if when we do this, there's at least 10 failures. Now, if there's at least 10 failures, because failure is the smaller one, there will be at least 10 successes. You could do an easy one to start. How many failures would there be out of 100? How many failures would there be out of 100? If we have 15% failures and we take a sample size of 100, we'd expect 15 failures. Oh, that one passes. If we take a sample size of 75 and we have 15% failures, how many failures would there be? So if we have 15% failures out of 75, how many failures would there be? Great job. So that one also passes because there's at least 10. How about out of 50? If we have 50 trials, 50 sample size, then how many failures would we expect there to be? How many failures out of 50? You can just divide 15 in half or multiply it. How many failures would we expect there to be out of 50? Not enough. I like that right there were some points. I like the not enough. That is true. So over here, the smallest sample size you would say to use would be what? We could check 20 just for fun. The smallest sample size you would expect to use or say to use is what? Which of these was our smallest sample size that we're like, that would be good right there to use? Where we have enough successes, enough failures. 75. 75 is where we have enough successes, enough failures. You could check the success rate too by doing 0.85, which is the success rate, times 75 to see we have enough successes. You could also find the failures by subtracting that from 75, because remember, successes plus failures is equal to the total amount. And this is what we expect. We're not saying we will see that, it's just what we expect. So the smallest would be 75, and the success failure condition is met because both NP and NQ are greater than 10, so the success failure condition is met. That should be it right there. And there we go. Very good question going over the success failure condition right here. Let's see, look, I'm back to normal now. But that is just the success failure condition. N was the amount of trials they were doing or amount of observations they were taking. P is the success rate, which is 0.85. Q is the failure rate, which is 0.15, which is the complement of P. The notation is so huge to these questions. Like, write out your notation, know what P is, know what Q is. It's very easy to get mixed up with like P, Q, P hat, X, N, mu, mu P hat, mu P hat, or sigma P hat. So all these things right here. And then we had another one, right? The other question was looking at the histograms. Let's look at those histograms. 44, 53, Stat 201, Chapter 13, quiz, looking at the histograms. Let's find out that one question. Ooh, that's some skewed data. Pew Research. Pew, pew. Did that one earlier. Suppose that 30% of people in town complete the statement. Those are easy. Is this it? What is, I don't see it. Is it on the homework? Pew Research? Yeah, sure. Definitely, Shay. We just did that one if you were talking about mine. We just did it? Wait. Oh, is it the one we just did is look at the histograms? Is it this one? Oh, looking at the histograms. And let's share wants Pew Research. Oh yeah, let's do Pew Research. There's Gallup. Hey. Oh, thank you so much right there, Chase. Pew Research. All right, cool. We did this one early. Wait, is this the? We did this one. Where is it? Gallup regular conducts. Did I label it wrong? Oh, it's like identical to the Gallup one. Huh. Okay. As sample size increases, the mean of the sampling distribution stays the same. Bingo, Meredith. Great job right there. Just look at the formula right there because there's the formula on the screen for you. The formula on the screen shows that it's not impacted by sample size. Does that make sense? We put questions like that on the test too. So just mathematically right there, you are correct. It doesn't change. It's exactly the sample size. It doesn't matter. So it stays the same. The standard deviation gets smaller as sample size increases mathematically. So lots of good review right there. Good question/answer. Yep, it stays the same. So it's theoretically the same value. Pew Research. Thank you, Lachey. Okay, drop some more questions. We've done a lot of these today. See, this chapter's not that bad. Pew Research in 2018. 4703. Here we go. Pew Research in 2018 polled a random sample of 1,058 teens, blah, 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 about internet usage. 45.1 responded that they were online almost constantly, a fact of great interest to advertisers. Ooh, we're going to sell them stuff. Explain the meaning of the sample proportion being this in context of the situation. So it wants you to understand that this comes from a sample, which is an estimate of the truth. We're not doing confidence intervals right now. So the answer is going to be that the sample proportion right here, P hat, is an estimate of P. And so I wish they just said the sample proportion is an estimate of the truth. Does that make sense? That the sample proportion is an estimate of the truth. The sample proportion is not an estimate of, and the hat right there means sample. We're not trying to estimate the sample proportion with the sample proportion. The sample proportion is used to estimate the truth. Fundraising dinner, you got it. Let's do that one next. And so calculate the standard error. Now, standard error, and they explain it down here, is going to be an estimate of the standard deviation. So that kind of clues you in on what they want you to do. The standard error is the best estimate of the standard deviation, and it is based on a sample size right there. So I wish they just said the standard error is the best estimate of the standard deviation, and it's based on a sample size. So with this, it's very, very similar. This question is a little bit tricky. So they're trying to introduce some topics to you. Because if we don't know P, what is our best guess of P, which they alluded to? If you don't know P, what is your best guess of the truth? So if you don't know P, what is your best guess of the truth? P being the true proportion, like the true proportion of people who are on the internet all the time. If you don't know P, what's your best guess of the truth? What would be your best guess of P if you don't know P? Best guess of P would probably be P hat, because that's the sample proportion, which the first question alludes to, where it says right here that the meaning of P hat is that it's our best estimate of P. So this is what we learned from our samples. That's the best estimate of P. Then they say down here, the standard error is the best estimate of the standard deviation. So if you look at this right here, the standard errors formula is an estimate of the standard deviation using the sample. So if we know P hat over here, which was equal to 0.451, how do we get Q hat? How do we get Q hat? Very important things we always need to be able to do like that. So how do we get Q hat? What is Q hat? How is Brian finding Q hat right here? How am I getting this? 1 minus, exactly, Chase. P hat is 1 minus Q hat. Q hat is 1 minus P hat. P is 1 minus Q. Q is 1 minus P. Because if you saw this proportion in your sample, this is the not sample proportion. It's the complement. And so now we're just going to take these numbers right here. I think it was like 1,000. What was the sample size? Sample size is 1,000, 1,058. So sample size is equal to 1,058. So 1058, 0.451 times 0.549 square root. And now we go over here, drop in the values. 0.451 times 0.549 divided by 1058 square root. There's the value right there. Calculate to 5 decimal places. 1, 2, 3, 4, 5. I think that's right. As long as I carried everything out correctly. That looks to be too big, though. I think there's... No, it is bigger towards to the center of the distribution. Let me double check. I feel like that's too... No, it's too large. I know standard... Something I feel like went wrong. 0.451 times 0.549 divided by 1058. Yeah, something went wrong in the calculator. I've done a lot of questions like this. I was like, that's too large for the standard error. So I typed a math thing wrong. 1, 2, 3, 4, 5. So that's going to round up, majorly round up right there. Yeah, I know, Lachey, it's very easy to make errors like that. Did I put it in the calculator? I should have double checked right there. I was like, I've done a lot of these, and I know I know the size of standard errors I should see. Like, I was like, that's too large of a standard error. So, however I typed it in, just my knowledge of having done so many problems like this, I was like, no, it should be like 1 or 2%. Just having done the math for this so many times, I kind of know how it should turn out. So yeah, that's it's just usually when you get towards 1,000, you get a very small standard error, because as sample size increases, standard error gets smaller. Standard error being an estimate of the standard deviation of the sampling distribution. How much rounding do you give on that question? Like, if you had, I wonder if it would have given us it wrong if we entered in like 0.29. That's ridiculous. Come on. They look at, if you entered in 0.29, of course I'd give it that. Obviously I'd give that. Even if you entered in that, I'd give you the points. It's obvious you know the answer. You're not guessing values like that. Always carry your mathematics to the end. Like, when I'm doing these sorts of problems, I'm solving them inside of R. So the way I solve them is I go over here, and you're gonna open. So it's here's how I would solve it. 0.451. I would solve that as P, or that's P hat technically. P hat. Q hat is 1 minus P hat. And then the standard error of P hat is equal to square root of P hat times Q hat over N. N was something like, not M. N is equal to 1024 or something like that. And then we go there, and standard error P hat. So I think you can carry more decimals or anything else. It's 1058. And there's the answer, and we could carry decimals. And then what's even better is I could go here to round and round that to 5 digits. Or was it 5? 5 digits? 7 digits? Oh, yeah, it is 5 digits because it rounds to the 30 right there. So right there, that's 0. Good, it still gives it to us. So this is how I would solve it if I had to do it, because I like to write the code for it. And then as long as you put the numbers in and write the formulas correctly, you get the right answer. So, but I try not to do this too much for 201 because you're not using R, so you can't really replicate what I do. But I store my P hat, I solve for Q hat. Like, I don't even solve for Q hat. Like, I solve as little as I can by myself. I just assign the values, and then I say Q hat is 1 minus P hat. I say my sample size is this. The formula for the standard error of P hat is P hat times Q hat over N square root of the quantity. And then I just take the value that I found and round it to 5 decimal places, and then there's the answer. So that's why I love coding, because if you type the code the right way, the answers come out the right way. But you can make errors coding too. You go whoops, and you put a wrong value right there, and then the whole question turns out a little bit differently right there. Very similar, but a little bit differently. And like I said, if we had a much smaller sample size, something like this right here, you would see a much larger standard error. So I've seen a lot of these questions, so I was like, that standard error of 7% or 0.07 is too large for the sample size of that high. We should start seeing around 1 or 2% standard error. But that only comes with knowledge of solving lots of these questions. I wouldn't have caught my error had it not been that. Let's check out when they have an annual fundraising dinner. Let's find out about this annual fundraising dinner. Let's go to it. 55, 53, step 201, chapter 13, quiz. Oh, hey. Annual fundraising dinner. This is the Gallup. We did that one earlier. Check out earlier. I think it's got to be here towards the end. Final project. Is this it when they have their annual fundraising? No. Is it on the homework or the quiz? Is it Lachey, is it on the, or is it Lachey asked? No, Meredith asked, excuse me. It's on the quiz? Okay, it might be a different version of one of these questions. Sometimes they change the version, and it starts out when they have their annual fundraising dinner. Is this it? This is a little different. It's different, yeah. It might be. How does the question go afterwards? I don't think it's that one. I think it's this one. There it is. Yeah, it's this one. See, they do a different version. Okay. So this is a good question right here. And it's all about theory. So I have to generate a version of it. Okay. It's weird. There's different versions, so you have to find the version that they create. So it's got some randomness. When they have their annual fundraising dinner, they typically get donations from 95% of people at the dinner. To see what the donation rates might be in the future, they did a simulation using sample sizes of 20, 50, 100, or 200. So if you've been following along with questions like this, what do you think is going to be the issue if we have a 95% success rate? What is our failure rate? I know. No, we haven't done this one yet. Even though it's on the screen. What's going to be the failure rate? 5%, right? So where do you think this will start to look normal? With a 5% failure rate, it'll start to look normal where? At 20, 50, 100, or 200? At 200. So the reason is we're talking about the success failure condition right here, which states that we need at least 10 successes and at least 10 failures. So as Meredith, and excellent work, Meredith, as you figured out right there, you said the success rate was equal to 95%. With a success rate of 95%, the failure rate is going to be equal to 5%. Now, the reason we're focusing in on this one is because to have at least 10 successes, it's going to be more about the failure rate. If you're wondering how we got the failure rate is 1 minus p. So if p is 0.95, the failure rate is the complement of it right there. So if we were to take a sample size of 100, what would be the expected amount of failures? With a sample size of 100, which is going to be NQ right here, what is the expected amount of failures? 1 minus p is q right here. It would be 5 failures. So when we look at this, if we don't have enough successes, the distribution will look skewed. And you can see that right here where it starts to look skewed, and at 200, it looks more normal. So at smaller sample sizes, you don't get that normal shape. And the whole point of the central limit theorem is that if we meet it, then the distribution will be approximately normal. And these are the conditions we're talking about. Randomly sample, so we have to have random people come to the fundraiser dinner, less than 10% of all people. So maybe we have 10,000 people on our mailing list. So we'd say with 10,000 people on our mailing list, we invite 200. Do we meet the 10% condition right here? If we have 10,000 people on our mailing list and we invite 200, would that meet the condition right here of a less than 10% sampled, less than 10% sampled, less than 10% sampled? We had 200 people at the dinner out of our mailing list of 10,000, which it doesn't say. I'm just kind of appending to the question. Would this be less than 10% were sampled? So you want to solve this equation right here. Is that less than 10% were sampled? So that's 2%. Is that less than 10%? What do you think? Yes or no? Is that less than 10% sampled? This is the 10% condition, which it doesn't mention. And yes, this is met. So we're just checking all the conditions to study for the test. We'd randomly select the people to come to the dinner. We'd have to know it's less than 10% of all people, which they don't give the population size. We had to make that up to do a version of the question. And then last but not least, we need to have at least 10 successes, at least 10 failures. And that is only met when you have a sample size of 200, because with 95% success rate, you'd expect 190 to donate, and 5% failure rate, you'd expect 10% to not donate. So here you see, while they're talking about the approximate normal, as the sample size increases, the center of the histogram stays the same. So and that is from mu p hat equals p, and it becomes more normal. That's, you notice right here, the normal shape. And the standard deviation decreases, which they call the variability right here. And these simulations tell us this right here. So the standard deviation decreasing is, I'll show you the formulas here again. Let me bring up the page with the formulas. Oh, we have it on the screen right here. There's the formula right here for the standard deviation decreasing, because as sample size increases, standard deviation will decrease. And as sample size increases, what happens to p, or mu p hat, I should say. As sample size increases, what happens to mu p hat? As sample size increases, what happens to mu p hat? What happens to the center? It does nothing. So mu p hat, the second one over there, this one, the second one we talked about, it stays the same. That's what they're saying right here. So I'm going to try to connect these ideas. When they're saying it stays approximately the same, they're talking about this. When they're talking about it decreasing, they're talking about that. So mu is the average. The center of the distribution remains approximately the same. So that is the mu p hat right there, stays about the same, where the variation getting smaller due to the larger sample size is going to be the standard deviation. So that's where it's talking about the variability decreases as sample size increases. So it says as sample size increases, variability is going to decrease. As sample size increases, the mean is going to stay the same. Does that make sense? I hope connecting this right here. So there's the mean staying the same, and here's the standard deviation getting smaller as the sample size increases. And then also we can see the shape getting more normal when you meet the at least 10 successes, at least 10 failures. And the simulation does appear to show this. Really good theory question. That's why, I can show the answer, but knowing the theory behind it and knowing how the equations work is the key to know that the mean of the distribution is always the mean. It's the true proportion. That's not going to be impacted by sample size. And then know that the standard deviation gets smaller as sample size n increases, because it's the formula p times q over n square root. Then, of course, the distribution becomes more normal, and that's due to the central limit theorem, that we start to have at least 10 successes, at least 10 failures. Any other questions? We've done a lot of them here today. What other questions? Win the fundraising dinner. Yes. Great job right there, Jackson. Let's do it. Good stuff. A little chill music. Chapter 13 quiz. Here we go. Yeah. No, let's do it right here. I think it's right around here. Okay. That's wrong. For the fundraising. Oh, I think it's is this it when they fundraising? Yeah, I think it's it. It typically gets. So is this the one right here? Besides, is this it when they send out the fundraising letter? Is this it, Jackson, or is it different? This looks like it? Okay. So you're right. It's the same sort of idea. So as sample size increases, what happens to the mean of a distribution? As sample size increases, and look at the formulas, what happens to the mean of a distribution as sample size... Yeah. And so what happens to the mean of a distribution as sample size increases? The formulas give the answer. Well, the mean will do what? The mean as sample size increases, so look at the mean of the distribution, and then look at the formula for it. The mean will do what? So do you see sample size? Sample size is over here. So what happens to the mean? The mean of the distribution as sample size increases will do what? So the mean of the distribution right now is P. Does that have anything to do with sample size? It'll stay the same about. Yeah, because it's the sample size.
It doesn't matter.
The formula is, let me ask you this. If I were to talk to 100 UT students and 60% of UT students were born in Tennessee, what percent of UT students would you expect to be born in Tennessee? So 60% of UT students are born in Tennessee. If I talk to 100, what percent would you expect to be born in Tennessee? Percent. What percent would you expect to be born in Tennessee? 60%. If I talk to 200, what percent would you expect to be born in Tennessee? So remember, 60% of the UT students are born in Tennessee. If I talk to 200 students, what percent would you expect to be born in Tennessee? 60%. So if I talk to 1,000 students, what percent would you expect to be born in Tennessee? 60% of the UT students are born in Tennessee. If I talk to 1,000 UT students, what percent? 60%. So notice you're just saying, well, if 60% of students are born in Tennessee, I'd expect to see about 60% in your sample. Does that make sense? This is the expected sample proportion. You expect to see the truth. So it's like, well, the most likely thing to see is if 60% of UT students are born in Tennessee, the most likely thing to see if I take a sample is 60% of students born in Tennessee. But what does change is the standard deviation. The standard deviation gets smaller as the sample size gets larger. Because it's in the denominator of the equation, making this larger makes the other quantity smaller. So that's what they're getting at right here with this question, is that the center of the histogram, which is the mean of the distribution, stays approximately the same. The shape of the distribution becomes more normal as we start to meet. Exactly. As sample size increases, mean doesn't change. It's not part of the formula. Standard deviation gets smaller. And you can actually see the standard deviation getting smaller here. It goes from 0 to 0.25. And at the larger sample size, it goes from only 0 to 0.15. If you look at what the center of this is at, it's at about 0.05. And the simulation does appear to show this. The variability is decreasing and the shape becomes more normal. And it's a good question theoretically. Check out the other version. We go into a lot of detail on it. But good theory question about how the mean stays the same, the standard deviation gets smaller, and it really goes to understanding this formula. And then the conditions right here are about how if we meet the conditions, then it will be approximately normal. So that's why we use the central limit theorem right here. You're welcome. And a lot of big notes today, and we don't do margin of error right now. There's central limit theorem again. There's the large enough. Yeah, literally, we got through over half the notes, and we just have this right here. We did pretty much everything today. We just have to talk about one more math formula, and then that's everything on the test and all the conditions. What do you think condition 1 is for the next chapter, for chapter 14? Condition 1, random. Condition 2, less than 10%. Condition 3, large enough. That one's a little bit interesting. The large enough sample size means we have to have a sample size that's large enough that the distribution of the mean will be approximately normal. The third condition is usually the tough one to go over. And if you notice, as we get larger sample sizes, the distribution starts to become more normal right there. So that's the large enough condition right here, that if we have a distribution that's skewed, if n is large enough, then the distribution of the sample mean will be approximately normal. So that's the way it works. And there's the formulas for the next class. Just like mu p hat equals p, mu y bar equals mu, and just like standard deviation of p hat equals p times q over n square root, the standard deviation of y bar is sigma over square root of n. So that is next class. Next class right there. We'll talk more about the central limit theorem and the sampling distribution of the sample mean. These are tougher chapters. But the practice and getting them down, knowing the notation is the key to the test, and being able to look at a question and say, what is it asking? It says sample mean is this, sample proportion is this, know the notation, know the notation. So with that, we might end off. Any other questions right now? I'll head over to Spoice. What other questions are there right now? Did my person contact me back? I don't see from my person yet. 1 p.m. Central. I am free. Central time. There we go. We're going to see to meet. For the final project, Stacey plans on sampling random students. What are you laughing? For the final project, let's go grab this. Okay. We're going to get the Mount Pearson thing fixed up. 11043, Stat Tool 1, Chapter 13, quiz. This is the second time that has happened. What has happened, Jackson? What happened? Here we go. Let's check it out. We keep posting the same question at the same time for the nice. For her final project, Stacy plans on sampling a random sample of 80 students on whether they plan to go to Florida or spring break. Great minds right there. So going to Florida, is that a categorical or quantitative question? Remember how we talked about how to solve stuff today? First thing you do is figure out if it's categorical or quantitative. Is going to Florida cat or quant? Like you either go to Florida or not go to Florida. That's categorical. So this is sampling distribution of sample proportion if it's going to talk about that kind of stuff. Remember, that's key to knowing what formulas to use, because if it's categorical, that means it's proportion. The proportion of students who go to Florida, even though proportion is a number, the question, did you go to Florida, is categorical, but summarized by a number, the proportion who go to Florida. For past years, she guesses that it's about 6%. So what quantity is she trying to guess right here? What quantity is she trying to guess? If she is guessing from past years, it's about 6%, and she's trying to think of the truth. This guess of the truth is what? This guess of the truth is what? If she's thinking, I think that's the truth. And she hasn't taken a sample yet. It's P. It is P. Great job. It's not, this didn't come from the sample. It's just a guess of the truth. She's saying, I guess the truth to be around 6%. So what condition would you check right here to see if it meets a certain condition? Remember, the conditions are randomly collect the data. Ah, look at that. Condition 1 is met. Maybe she's got a lot of friends. She goes to UT. Stacy goes to UT. So are 80 students less than 10% of 33,000? We're good on 10%, right? So she's sampling less than 10% of her UT friends. We're assuming she goes to UT. Safe assumption for this question. So Stacy goes to UT. 80 students would be less than 10% of all students. So we probably need to check the what condition right here. We probably need to check the what condition. We just checked random. It's met because she randomly took the students. We checked less than 10% because her sample size of 80 is less than 10% of all the students. She's sampling less than 10%. The final condition is what? Now you have to think what your data is. Is it categorical or quantitative? The final condition, which is on the screen if you're looking at your question, is the what condition. What is the final condition? The final condition is known as the what condition. Pass fail. You can call it pass fail. Success. We call it success failure, pass fail. And so we check that by doing NP is greater than or equal to 10, and Q is greater than or equal to 10. Now you could find Q right here, but Q is the bigger one, so that's not where the problem's going to be if there is one. There is one. Right here. So which of these quantities is less than 10? And so if it's less than 10, you fail the condition because you don't have at least 10 successes, at least 10 failures. So I'm trying to think through. I think it's going to be 4.2. Is that correct? Someone correct me if I'm wrong. I think it's 4.8. 4.8, I think. Is the quantity 4.8? How did you get that? The answer is 4.8 is less than 10. We fail the condition. How am I getting that? Start plugging in the values. Does this make sense? We fail because 4.8 is not enough successes. So she can't use the normal model to model this. If you take a look at what would happen, I think I still have it up. Do I? No, I don't. If you take a look at what would happen with this binomial distribution, what it's going to look like with a sample size of 80 and a success rate of 6%, it doesn't look that skewed. It is still skewed, though. The smaller the sample size, the more skewed, or the smaller the expected amount of successes, the more skewed it is. She doesn't pass because she has 4.8 expected successes right there. You need at least 10 expected successes. And if you were to have 10 expected successes, it would look approximately normal. And these are the conditions we have to meet: random, 10%, and success failure, at least 10 successes, at least 10 failures, such that the distribution of the sample proportion is approximately normal. So no, because the success failure condition is not met. So that would be it right there. Select all that apply. Yes, because no. Because the data doesn't meet the quantitative data condition. No. 10%, assuming she has sampled, goes to a decent sized place. Nearly normal is for quantitative data and randomization condition. She randomly selected, so it should just be the success failure right there. There we go. This is the condition. The nearly normal or large enough n is going to be the condition for quantitative data, which if we're doing distribution of the mean, it'd be quantitative. But this is not quantitative data. Well, with that, we're going to see if my Pearson's got everything going. Until then, Jackson, Lachey, great work and great job on those people getting above a 90. This is a tough quiz with lots of questions. Keep up the great work. Bye for now. Bye.